Hello everyone, welcome to the video. Today we are going to solve the problem minimum number of jumps. In this problem, we are given an array of integers and every element in this array represents the length of the maximum jump that we can make. For example, the number 3 here indicates that we can jump till 5, till 8 and even till 9, but not beyond that. So this is given to us and we have to return the minimum number of jumps that are needed to reach the end of the array. And if any of the element is 0, that means we can't move through that element. We can't jump any position from that element. In case we can't reach the array, we have to return -1. So we will solve this problem today. We will go through the thinking process, write the algorithm, and then also see a working code for it. Later, we'll also see how to return the actual path followed for minimum jumps and not just the minimum jumps required. But before we start, if you are new to this channel, please don't forget to subscribe. Let's start. To begin with, let us first note down the key things given in the question. We are given that there are n integers. They are present in an array. And every element of that array represents the maximum length of the jump that we can make from this position. And what we have to return is the minimum number of jumps that we need to reach the end of the array. It is also given that if the element is 0, then we can't jump from here. And if it is not possible to reach the end of the array, we have to return -1. If we consider this array as an example, then here to reach the last element, we will need to make at least 3 jumps. For example, first jump till 3, second jump till 9, and then third jump till last element of the array. So if we consider our solution as a black box, we are getting an array as an input and we have to return the minimum number of jumps. So what will our function signature look like? Our function signature will look something like this. Let's start thinking about the problem. Now our aim is to reach the end of the array in minimum jumps possible. So we may think that from every point we should jump the maximum possible so that we can reach the end fastest. For example, here we could jump at max 1 step. So we jumped here. Here at max we could jump 3 steps. So we jumped till here. And here at max we could jump 9 steps. So we could reach our end of the array. But will this approach work always? This will not work always. Because consider if instead of 9 we had 1 in its place. Then using this approach from 3 we would land directly to this position. But now 1 is a very small number, so at max we can jump here. Therefore, using this approach, reaching till 9 will take more than 3 jumps. But if instead of jumping till here we had only jumped till this position 8, then in the next jump we could have reached the end position 9. Therefore, this greedy approach is not working always. Since our greedy approach is not working, let us think some more about this problem and make some observations. So our aim is to reach the last index. Let us call this index as I. Now, to reach this last index, we will have to make jump from any previous index. For example, we can jump from here or here or here or here. So this is our first observation. So this is pretty simple, that to reach an index I, we will have to make a direct jump from some index j such that j is less than I. J can range from this to this anywhere. But another thing is needed. To jump from any particular index j to I, the value at that index should be greater than the number of steps remaining to reach I. So this is our second observation, that the value at that particular index should be greater than or equal to this gap I minus j. For example, we cannot jump from here because from this j we can at max jump 2 steps. but we can jump from any of these j's because each of these values are greater than the gap between I and j. Now, we are starting from first position. So to be able to achieve this, first prerequisite is that this j position itself should be reachable. It should not be unreachable. We denote unreachable position by returning the answer -1. So if for a particular position j, to reach that position j, if the answer returned is -1, that means that j cannot be reached. So this condition should be satisfied, that the answer for j should not be equal to -1. Now, there can be many j's which satisfy these conditions. They are reachable, we can make a direct jump to I from that j, and they are prior to I. So which of these j's should we choose? Since our aim is to get the minimum number of jumps, we should choose the j which gives us the minimum number of jumps. So this is our fourth observation, that for all such j's which satisfy these three conditions, if we have the answers minimum number of jumps to reach j, then we should choose the minimum of them, because minimum of them +1 will be our answer. +1 because we also need a direct jump from j to I. From the observations, we can note one thing, that we were looking for minimum jumps to reach I, and it is dependent on minimum jumps to reach j, where j is smaller than I, and our input is this nums array. So if we have to reach j, that means our input is getting smaller. That means our final answer is dependent on answers to smaller problems. That means we are trying to solve this by recursion. So let us now try to express our original problem and smaller problem in a recursive relation. So if we are representing our original problem as minimum jumps required to reach the position I, then how will we calculate it? We will check for all j which are less than I. If aj is greater than equal to I minus j, that means a direct jump from j is possible, and minimum jumps till j is not equal to -1. That means j is reachable. For all such eligible j's, we will check what is the answer for reaching j. What are the minimum jumps required to reach j? And that +1 is our possible number of jumps to reach I. But since we are looking for minimum, we will look the minimum of such values, and that will be our answer. So this is our recursive relation. Now we have the recursive relation, so we can try to convert this into algorithm. So this is our recursive relation. And as with any recursion problem, we will go through writing the algorithm step by step. Our first step was identifying the recursive relation, which we have already done. Our second step was identifying the inputs that will go into the recursive method call that will call itself again and again. So this is our recursive method call, and the inputs to it will be an index I where we have to reach, and the array itself. We need the array because in the recursive relation also we need the array. So what does this function signature represent? This will calculate the minimum number of jumps required to reach the index I and will return it. Now, before moving to these steps, let us try to first convert this recursive relation into algorithm and write it down. Since we have to see for all j which are less than I, we will have to iterate from I minus 1 till 0. Now in every iteration, we will be at a particular index j. For that particular index j, we will have to check these two conditions. So let us first check if the j is reachable. To check if that j is reachable, we need answer for j, minimum jumps for j. So we call the same method with input as j to find out what is the number of minimum jumps required to reach j. And if that answer is not equal to -1, that means j is reachable. But then we have to check the second condition as well, that if there is a direct jump possible from j. So we check again that if arrj is greater than or equal to I minus j. If this condition holds true, then there is one possible answer from position j. That answer will be equal to the number of jumps required to reach j plus 1. But this is not our final answer. Our final answer will be minimum of all such candidate answers. So we need another variable to track the minimum that we have seen so far. So we have this another variable minimum jumps so far. We initialize it with plus infinity. And whenever we see a candidate answer which is less than the minimum that we have seen so far, then we update the minimum that we have seen so far. In this way, we can iterate through all j's and have the answers corresponding to all possible j's, and also keep track of what was the minimum one. So if minimum jump so far is still equal to plus infinity even after going through all these iterations, what does that mean? That means there was no j which could satisfy these two conditions, and that means this I position is unreachable. So minimum jumps so far will be equal to -1, and finally we will return minimum jumps so far. If this condition was not reached, then this variable would store the minimum jumps required to reach I. So this way we have translated our recursive relation into algorithm. But is this complete? No, this is not complete, because here this same method will keep on calling itself and it will go into infinite recursion. So we need something called base or terminating condition to terminate this recursion. And when is base or terminating condition reached? It is usually reached when our input is smallest. Our input I becomes smallest when I is equal to 0. And what does I is equal to 0 mean? It means we are looking for minimum number of jumps needed to reach the 0th index when we start from 0th index. Its answer will obviously be 0. So we add this base condition that if I is equal to 0, return 0. Now at this point, this algorithm is complete and it will work fine. But it has a very high time complexity. Why? Because there are still many overlapping problems. Same problems are being solved again and again. How? Consider this example. Here we have to find the minimum number of jumps needed to reach this 10th index. Now as per this recursive relation, to find the minimum number of jumps needed to reach the 10th index, we will need answers for 9, 8, 7 and so on. And if we keep growing this recursion tree, it will look something like this. To solve for index 9, we will need answers for index 8, 7, 6, 5 and so on. To solve for index 8, we will need answers for 7, 6, 5 and so on. And this way this recursion tree will grow. So what can we observe here? We can see that there are many overlapping problems. Example, index 8 is overlapped twice. Index 7 is overlapped thrice in just this visible part of the recursion tree. That means, as per the algorithm on the previous slide, we will be calculating for the same input again and again. And this is the case when input is very small. If the input is very large and recursion tree grows very dense, then we will have a lot many overlapped problems, and each of those problems will be overlapped multiple times. So what to do about it? How can we solve? We can do one thing. Whenever we solve for an input, we store its answer in some storage. And whenever we see the same input again, instead of solving it again, we just go to that storage and return our answer from there. So we basically need to store the information like that for a particular index I, this is our answer. Which data structure can we use to store this information? We can use a map. In map, we can get a value by a key in just constant time, big O of 1. So we can use map here. But for map, we also have to define the data types of key and value. Here, key is the index, so it is simply integer. And answer is just the number of minimum jumps, so it can also be integer. So let us see that how do we modify our algorithm with the introduction of this map. So we will have a new parameter map that will be passed to our recursive method. And whenever we are calling this recursive method, we will add this parameter map. Now, before returning the answer, we will put our answer in the map against that index. And whenever we encounter any input, we will first check if we have encountered this input in the past. So we will first check if this input is present in the map. If this index is present, then we will return the answer directly from there instead of recalculating it again. Now we have solved the problem of overlapping problems and our time complexity has reduced drastically. So what is our time complexity and space complexity now? Our time complexity is big O of n square. Because for every position in the array, we have to iterate again for all indices which are prior to that position. Therefore, the time complexity is big O of n square. And space complexity is big O of n because our map contains the answer for every index and n is the length of the array. So this completes our top-down dynamic programming algorithm to calculate the minimum number of jumps. Let us now go through the code for the same algorithm that we just discussed. You can also find the link to this code in the description. So this is our main function, minimum jumps. It takes an array as an input and it returns the minimum number of jumps required to reach the last index of that array. So first of all, we get the array's length. We also declare a map of integer and integer. This map is supposed to store the results for every index. So we call our recursive method. We call our recursive method with I is equal to n minus 1 because initially we have to reach at index n minus 1. And whatever is the answer for this will be our final answer. Now let us see how does our recursive method look like. In our recursive method, first of all, we have this base condition that if I is equal to 0, then return 0. This is because I is equal to 0 corresponds to 0th index and we are already at 0th index in the beginning. So we don't have to jump anymore. Then we check in the map if we have encountered this input before. So we check for the key which corresponds to index I. And if we have encountered this, then we return the answer directly from the map. But if we have not encountered, then we have to solve for it. And to solve for it, we have to iterate for all j's that are prior to I. And in every iteration, we first calculate the answer for the index j. That means minimum number of jumps required to reach j. If that is not equal to minus 1, that means j is reachable. Then we have to check further condition that is there a direct jump possible from j to I. So we check if arrj is greater than equal to I minus j. If this is possible, then there is a possible answer via j. And that possible answer is minimum number of jumps required to reach j plus 1. But that is not our final answer. Our final answer will be minimum of such possible candidate answers. So we have a variable minimum jumps so far to keep track of the minimum. We initialize it with plus infinity. And whenever our candidate answer is lesser than this minimum, we update our minimum. But if this minimum still remains to plus infinity, that means there is no j from which reaching to I is possible. And that means I is also unreachable. So we update minimum jumps so far to minus 1 because minus 1 denotes unreachable element in our case. So we return the minimum jumps so far, but before returning, we put our answer in the map against that index. So this completes the code for returning minimum number of jumps required to reach the last index of an array. So far, we have been focused on calculating the minimum number of jumps required to reach the last index. But there could be an extension to the problem as well. Instead of returning the minimum number of jumps, we could be asked to return the jump path. For example, here the jump path looks something like this. We jumped from 0th index till first index, then first index till 4th index, and then 4th index till 10th index. So how will we solve this? Let us see if we had any information about the minimum jump path when we are calculating the minimum jumps in this algorithm. Yes, we did have, because for any index I, we knew what j we should choose. We should choose the j for which the answer is minimum and which satisfies this condition. So we knew that before reaching I, what was the previous position in this jump path. This gives us a hint that maybe if we have this information saved somewhere, that to jump to I, which j we are using, then maybe we can reconstruct the path. So we basically need to store this information, that to reach index I, we used previous position as j. And we can store this information in another map of integer comma integer. So if we consider this example, the information we will have stored in this map is this, that to reach index 10, we will jump from index 4. Similarly, to reach index 4, we will need to jump from index 1. And to reach index 1, we will need to jump from index 0. So if we have this map, we can definitely trace back the path that we followed. So how will we convert this map to this path? Let us try to write the algorithm. Clearly, we need to iterate. In every iteration, we will identify an index which is part of the path, and we will iterate till we reach the index 0. So let's call it by the variable path index. So the first index that will be part of the path is the final index that we need to jump to. For example, and it will be always n-1. So we initialize from here and then we iterate. In every iteration, we will push this path index onto a stack. Why are we using a stack here? Because first we are getting the information about the last elements in the path. So we can push that element in the stack. And then we need to figure out what is the next index or the previous index in the path. To find the previous index in the path, we can make use of this map. And from this map, we can get the value for this current path index. So if we give 10 here, we will get 4. And the next iteration will be for 4. Then we will push 4 here. And then again, against this 4, we will get the value 1. Then the next iteration will be for 1 here. We will push 1 in this stack. And then here path index will become 0. And as path index becomes 0, this iteration will stop. So at the end, we can push 0 onto the stack as well. Then we can simply convert this stack into a list and return. This is the way we can solve the problem of returning jump path along with the minimum number of jumps.
This is it for this video. If this video was useful to you in any manner, please let us know by commenting below. Also, let us know in the comments what will be the next problems that you would want to see on this channel. Please don't forget to like and share the video and subscribe the channel. We will meet again in the next video with some other problem. Thanks for watching.